Hello and welcome to my science tutorials. In today's video we are going to be looking at resistivity. So without wasting much time, let's get started. So what is resistivity? Well, before we look at what resistivity is, let's have a look at this general observation about metals as wire. So metals in the form of wire, okay, they offer some resistance to the flow of current through them, okay. So this resistance, okay, the resistance offered by a metal wire, okay, is proportional to the length L, okay, and then inversely proportional to the cross-sectional area. So the resistance of a wire is proportional to the length and then inversely proportional to the cross-sectional area. Now whenever we remove a proportionality sign, we tend to introduce a constant, okay. So in this case, when we take off the proportionality sign over here, okay, we have the resistance will be equal to, then we introduce a constant. That constant is what we call the resistivity, and then it is represented with this symbol, okay. So we have the resistivity, then we have the length, and then the cross-sectional area, okay. So from here, if we make resistivity the subject, okay, if we make resistivity the subject, here will be 1. So we have resistivity times length is equal to what? Resistance times cross-sectional area. So we divide both sides by length, okay. So we have our resistivity being equal to what? The resistance times the cross-sectional area divided by the length, okay. So mathematically, the resistivity of a wire is the product of what? The resistance times the cross-sectional area divided by the length, okay. So this is the formula for finding the resistivity. But then we also need to take a good note of the fact that we are talking about wire, okay, wire in this case. And so for wire, to find the length, we can measure the length times the breadth and saying we are using that to find the area. It's not possible. So we have another formula that is used to find the area of things like this, okay. So in this example, the wire, we can get the diameter, okay, we can measure the diameter, okay. So once we can get the diameter, then we can use the formula area is equal to what? Pi d square divided by 4, okay, as our area. Now if this is, let's say, equation 2, and then this is our equation 1, then what are we going to get? If we substitute this in place of this, we are going to be getting what? Our resistivity to be what? R pi d square, all divided by what? 4L. So the resistivity of a particular wire, okay, a particular conducting wire, when when we know the area and then we don't have the diameter, we can use this formula, the equation number 1, to solve and get our answer. But then once we know the diameter, we can, and we know the resistance, and we know the length of the wire, we can use this also to get the resistivity of the wire, okay. So let's have a look at some few examples to actually appreciate what we are talking about resistivity. So let's look at example number 1. So let me quickly get rid of everything over here. So example number 1, we have here, calculate the resistance of a coil of copper wire of length 2 meters and a cross-sectional area of what? 0.44 meters square. Sorry, this is supposed to be 0.04 millimeters square, okay. So sorry about this. Okay, so calculate the resistance of a coil of copper wire of length 2 meters and cross-sectional area of 0.04 millimeters square, given that the resistivity of the copper wire is 1.72 times 10 raised to the power minus 8 ohm meters. Now this is something I forgot to tell you. The SI unit of resistivity is ohm meters, okay. So the resistance divided by resistance multiplied by the distance, so it's ohm meters, okay. So with this, let's look at how to solve this problem. So we have here a solution, okay. So we have to calculate the resistance, so it means we don't know the resistance, okay. then of the coil wire of length, so we have length is 2 meters. Mind you, the length is in meters, okay? Then the cross sectional area is what? 0.04 millimeters square. Okay, so millimeters is like is times 10 raised to the power what? Minus 3 meters. Okay, so if we square them to get millimeters square, okay, if we square this side, then we square this side, we get what? Millimeters square over here. Then this will become what? 10 raised to the power minus 6 meters square. Okay, so to convert from millimeter square to a meter square, this is the conversion. Okay, so from here we can see our area is equal to what? 0.04 times 10 raised to the power minus 6 what? Meters meters square. Okay, so now that we have our, we don't know our resistance, but then we know our length, we know our area, and we know our resistivity, we can simply solve for resistance. And like I said, resistance is proportional to what? The resistivity times the length all over what? The cross sectional area. So our resistance will be equal to what? The product of the resistivity, which we have over here, 1.72 times 10 raised to the power minus 8 ohm meters, okay, times the length. The length is what? 2 meters, all divided by what? The cross sectional area, which is 0.04 times 10 raised to the power minus 6 meters square. Okay, so one of the meters will cancel one over here, another one will cancel this, so the 2 meter the meter square we have over here gets rid of this and this, so at the end we are getting ohms, which is the unit of what? Resistance. So our answer over here is, let me quickly punch this into the calculator. So we have 1.72 times 10 raised to the power minus 8 times 2 divided by 0.04 times 10 raised to the power minus 6. So this is giving us 0.86 ohms as our answer. So yeah, this is how we, when we have a question like this is how we can solve for the resistance. So let's have a look at another example where we will be given the resistivity, then the resistance, and then the diameter, and then we are asked to find other parameters apart from the resistance or the resistivity. So okay, so example number 2. So the resistivity of a constantan wire of diameter 0.54 millimeters is 4.5 times 10 raised to the power minus 7 ohm meters. Calculate the length of the wire needed for the construction of what? 5 ohms resistor. So solution, let's jot down everything we know. So the resistivity of a constantan wire of diameter, so the diameter is what? 0.54 millimeters. Okay, now the resistivity is what we are given over here. So we have the resistivity to be what? 4.5 times 10 raised to the power minus 7 ohm meters. Now we have to calculate the length, okay, L, we don't know, needed for the construction of what? 5 ohm resistor. So it means our resistance that we end to construct at the end of this thing is, it should have the resistance of what? 5 ohms. Okay, so it's like we are not supposed to find what? Length in this case. Now remember we said resistance, okay, is equal to what? The resistivity times length all over what? Cross sectional area. But because we don't know the area and we are given diameter, it means our area is equal to what? Pi d square all over 4. So if this is our equation 2 and this is equation 1, if we substitute this into equation 1, what are we going to get? We will get what? We will get our let's cross multiply over here. So we get our resistivity times length to be equal to what? Resistance times area. Okay, so we divide by resistivity. Okay, so we get our length to be equal to what? Resistance times area all over resistivity. But then from here we know our area is what? Pi d square over 4. So our length is equal to what? Resistance, then pi d squared all over what? 4 times the resistivity, if you do the substitution very well. this is what you will get. So from here we can straight away get our length. So we have our resistance to be 5 ohms times pi times d squared. The d is 0.54 times 10 raised to the power minus 3. So that's the conversion to meters. So millimeters, milli is times 10 raised to the power minus 3. So we square here as the d is squared over here. So 4, then we have the resistivity, which is 4.5 times 10 raised to the power minus 7. Okay, so let me quickly punch this into the calculator. So we have 5 shift pi, just to get a pi on your calculator. So shift and you press the pi. So 5 times pi times 0.54 times 10 raised to the power minus 3 all squared divided by 4 times into bracket 4.5 times 10 raised to the power minus 7. So yeah, this is giving me 2.54 meters. So this means if you want to construct a resistor, okay, to have a resistance of 5 ohms, and then we are using a constant wire, it means we need to cut the constant wire to have a length of what 2.54 meters. Okay, so when we cut the constant wire, we have the length of 2.54 meters. It means per this resistivity, and then the diameter of our length of our wire is 0.54, and then the resistivity of the constant wire is this. Once we cut the length of what 2.54, our resistor, okay, the wire will offer a resistance of what 5 ohms, which is what we want in the circuit that we are going to use. Okay, so this is how we solve problems on resistivity. This is an extension of what direct current, and then in the next video we will probably be looking at Kirchhoff's law, where we tend to look at how to use loops to solve more problems. So thanks. Hello and welcome to my science tutorials. Today we are going to be looking at temperature coefficient of resistance, which is denoted by the symbol alpha. So without wasting you guys your time, let's get started. Okay, so what is temperature coefficient of resistance? Well, temperature coefficient of resistance is the quantity that shows how resistance varies with temperature. Okay, so whenever we have a conductor, or we have a circuit, okay, laid down, and then we have current flowing through the conductors, okay, depending on the particular conductor, okay, as the temperature changes between between when the cell is connected and then current begins to flow, temperature changes. Okay, so when the temperature begins to change, depending on the nature of the conductor, okay, the temperature can either go high or low. The resistance can either what go high or low. Okay, so these changes in resistance of a conductor, okay, as temperature increases, okay, is what we call the temperature coefficient of resistance. Okay, so the symbol is alpha, like I said, and then how is this given mathematically? Okay, so mathematically, okay, the temperature coefficient of a resistor, okay, of or resistance, mathematically is given by what RT minus what R naught all over what R naught times T. Now what is this RT, R naught, and then T? Now the alpha we have over here is what we are calling the temperature coefficient of resistance. Now the RT is what the resistance of the wire, okay, resistance of wire at what the temperature T. Okay, so the RT is the temperature of the wire at a particular temperature. Okay, now the R naught is what the resistance of a wire what at what temperature is equal to what 0 degrees. Okay, so in this example, normally for temperature coefficient, okay, we look at when the wire is at the temperature is 0, okay, the resistance of the wire, okay, and then when the temperature is at a particular temperature, I mean when the temperature has risen to a particular temperature, okay, maybe 20, 30, 40, okay, the resistance offered by that wire differs. Okay, so we are looking at the RT to be the resistance at that particular point when the temperature has either increased or decreased, and then the R0 is the temperature when the wire the temperature of the wire was 0 degrees Celsius. This is supposed to be 0 degrees Celsius, sorry about that. Okay, so R0 is the temperature at 0 degrees Celsius, and then RT is the temperature at that particular temperature that we are talking about, that the resistance of the wire is changing. Okay, so from all this explanation, the temperature coefficient over here has the unit. Okay, it has the SI unit of what, degrees Celsius inverse or Kelvin inverse. Okay, so depending on the unit that you are given in the question, you can either decide to maintain it as a degrees Celsius inverse or Kelvin inverse. Now this equation looks a bit more complicated, you know, it's a little bit raw, so let's try and make it beautiful. Okay, so let's try to make R0 the subject over here. Okay, so let's make R0 the subject. So we tend to cross multiply, so we have R total minus R0, the top one, will be equal to what, alpha times what, R0 T. Okay, but we want to make what the subject, RT, sorry, let's make RT the subject. So we want to make RT the subject, so we have RT is equal to alpha into bracket R0 T, okay, then plus R0. So we brought this one to the other side of the equal to sign, so we have RT again is equal to, now we have R0 here, R0 here, so we can factor out R0. Okay, so if we factor out R0, we have alpha T plus, here will become 1. Okay, so if you multiply this, you will get what, alpha R0 T plus then R0. Okay, so this is the equation we'll be using mostly to solve any example on what, temperature coefficient of resistance. So the resistance at a particular temperature is equal to what, the initial resistance of the wire at 0 degrees Celsius times the temperature coefficient of the resistance times the temperature plus 1. Okay, so this is the formula we are going to use to calculate for either maybe the resistance at a particular temperature, or maybe the resistance at 0 degrees Celsius, or maybe even the temperature. Depends on what the question has given to you and then what the question is asking you to find. So with this basic introduction and this basic understanding, let's have a look at some series of examples to actually understand what we mean by the temperature coefficient of resistance. Now this is actually interesting, so I will take my time and explain everything. Now they say the resistance of tungsten filament, okay, at 1750 degrees Celsius is 4 ohms. Find the resistance of the filament at 20 degrees Celsius. Now this is interesting. The temperature of the filament, okay, at a particular point in time was what, 1750, and then we are supposed to find the resistance of that filament, okay, at 20 degrees Celsius. So you can see we have different 2 RTs, okay, different temperatures, and then what we don't have in this case is what, the temperature at what, the resistance at 0 degrees Celsius, which is the R0. We don't have the R0 over here. So before anything else, we need to use the first scenario to get our R0, and then use that R0 in solving for the temperature at 20 degrees Celsius. Okay, now we are given the temperature coefficient of resistance of the tungsten to be 6 times 10 raised to the power minus 3 Kelvin inverse. Okay, now because we are given this in Kelvin inverse, we need to change any other temperatures we have over here into Kelvin. Okay, so let's look at our solution in this example. So solution, so the resistance of a tungsten filament at at this temperature, so T1 is equal to what, 2750, okay, so degrees Celsius into Kelvin, we just add 273, so 273 plus 2750, 273 plus that will give us what, 2023 Kelvin. Okay, so the second temperature T2 is what? 20 degrees Celsius, and then so this one will be what? 20 plus 273, and this will give us what? 293 Kelvin. Okay, so let's write the expression for the first example. Okay, so if we have RT, okay, let me use RT1, that is the resistance at temperature 1, which is the 2020 Kelvin, will be equal to what? The R naught, okay, into bracket alpha T1 plus what? 1. Okay, so this is our equation 1. Now the RT2, okay, at 20 degrees Celsius, okay, this will also be equal to what? R naught into bracket alpha T2 plus 1. So equation number 2. Can we see that the only difference between these two equations, okay, is the fact that their resistance will be different, and then their temperatures are different, but then the temperature coefficient of resistance is the same, and then we still have 1 over here. So let's find a ratio between these two so that we can get rid of the R naught in this instance, okay, so that we can find the RT2, which we are supposed to find in this case. So let me say equation 2 divided by equation 1. Okay, so we have RT2 divided by RT1 will be equal to what? The RT2, we have R naught into bracket alpha T2 plus 1 divided by R naught into bracket alpha T1 plus 1. So this can cancel this. Okay, so let's make RT2 the subject. So RT2 will be equal to what? This whole thing, the ratio over here, times RT1, which is what? Or RT1, okay, into bracket alpha T2 plus 1, this is plus 1, all over what? Alpha T1 plus 1. So from here straight, okay, we can input everything we have, and then we get our answer. Okay, so the RT1, okay, is the resistance at temperature T1, and this is given to us by as the 4 ohms we have over here. So we have 4 into bracket the alpha is what? 6 times 10 to the power negative 3, okay, times the temperature at T2, okay, is 20, which is what? The 293 we have over here. So it's 293. So this plus 1 all divided by 6 times 10 to the power minus 3. Then the temperature at this instance is what? 2023. So times 2023, okay, then plus 1. All right, so let me get some space over here. So our RT2 will be equal to, now if you input all of this into your calculator, you'll be getting 0.84 ohms. Okay, so it means the resistance of the filament at the temperature 20 degrees Celsius or 293 Kelvin is equal to what? 0.84 ohms. Now if you don't understand this way of doing it, you can look at it in another way, okay? And then the other way is, let me bring this down a little. Now the other way we can look at this is the fact that from the first one, RT1 is equal to R naught into bracket 1 plus alpha T1, okay? We can input the RT, which is the 4 ohms over here. We don't know the R, we know this, and then we know the temperature over here, which is the 1750 or the 2023 Kelvin, okay? So we input this over here, then the alpha, which is this over here, then we solve for R naught in this example. So after we get the answer for R naught, it's just a matter of just putting the R naught into the second equation, which is what? RT2 is equal to what? R naught, okay, 1 plus alpha T2, and then we know the T2 to be what? 20 degrees or the 293 Kelvin, and then we know the alpha to be this, okay? okay, and then we now know the R naught which we obtained from this first scenario. Okay, so easily we can get the R2 from there. So if you don't understand the process I go through by getting the answer using this method, you can simply go by the normal way by finding the R naught first and then using the R naught in the second equation, or the second equation, yes, to find your RT2. Okay, so that is all I have for you guys in this video, and thanks so much for watching, and then